Yes, this is for your new unit.
Molecular transmission.
Theory. All right, that stands for kinetic molecular theory. As to review again for tomorrow's test, what did it say for tomorrow's test? Ah, you've already written it. You should know it. It's on the test tomorrow. You will see it somewhere in the multiple choice. All right, is the idea that particles in any sample of matter are moving. Now, when I say any sample of matter, what do I mean by that?
I mean, like the table.
That's right. I mean solids. I mean liquids and gases. So, when Eric said the table, I mean the particles in the table are moving. We mean particles in water or particles in air. So when we talked about this I guess it'll be about a week and a half ago now, several days ago. That's right. We said the particles in these pieces of matter would not stop moving until we got to what temperature?
Zero.
What zero?
Absolute zero.
That's right. All right. They don't stop moving until absolute zero.
So is nitrogen absolute zero?
No, it's not. Now, absolute zero is 0 Kelvin, which is negative 273 degrees Celsius or negative 457 degrees Fahrenheit. Okay? Now, right now, 0 Kelvin is a theoretical value. We've not reached that yet. Scientists have tried, but they've not actually gotten all motion to stop at this point. Now, that may happen in our lifetime, but right now it's not occurred yet. Now, that is all review. Everything that I just wrote on that board, you should already have in your notes in the gas laws at the very first part of the section. All of that is fair game for the test tomorrow. Yes, ma'am. I mean, you could convert to find it, but no.
So what does it start?
The gas laws start with KMT in your notes.
That's what it says starts, and then
And it ends with the thing we did yesterday with calculating using the volume ratios and then PV equals nRT. The test is literally 10 multiple choice and 11 word problems.
60 something.
It's 21 questions.
If I get 100, can I get $1?
No,
You can get 100.
Yeah.
no.
What if mine?
It has been a rough month for me. No, I'm broke. I've paid Uncle Sam $3,000 in taxes this month. I've lost a July paycheck with a change in the school calendar. And I've had to pay $600 in insurance that they were taking out of my check in July that I'm no longer getting. So no, I'm broke.
Me too. I just had a lot of minutes.
They said we could get that.
Well, that's what
All right.
I don't have a job, so I've never had a job.
I got a job.
$12 an hour. Exactly. I don't like that. I don't like that. Last time that I went in, we went in with Bryce. We got everything. I know I will. I actually don't do my phone. Exactly. Even a quarter letter time.
Alright, now, we want to talk about how solids, liquids, and gases, and I'm going to draw this on a different board. I'm going to make a chart. All right, but somewhere in your previous science background, someone should have drawn a picture illustrating for you how solids, liquids, and gases should look. Hopefully, someone talked about shape and volume for you. All right, so if we talked about a solid, liquid, and gas, which one of these three would have a definite shape? Okay. Who would have a definite volume? Would anyone else have a definite volume?
So, yes.
All right, I hear solid and I hear gas.
Yes.
Now, the problem with a gas is a gas will expand and it will take the shape of whatever container it's in. So a gas has an indefinite shape and it has an indefinite volume. So this part is review for your test tomorrow. Gases expand, all right? Remember, we talked about 5 properties that gases have. They have the ability to be compressed. They have the ability to expand. Because gases can expand and fill the container they're in, they do not have a definite shape and they do not have a definite volume. If you have a 1 liter gas and you put it in a 2 liter container, is it going to sit at the bottom in that 1 liter space? No, it will expand and fill the 2 liter space that you put it in. So it has an indefinite shape and an indefinite volume. Now, a liquid has an indefinite shape. All right, it takes the shape of whatever container it's in. If you have a bottle of water, it takes the shape of whatever bottle it's in. If you pour it out on the counter, it's going to lay flat on the counter or on the floor that you poured it out on. Okay, but a solid, if you have the shape of the calculator, it stays in this shape. It's not going to form a puddle of ooze on the counter when we set it down. It keeps that shape. Okay, everybody with me on that? Now, everybody got what they need off the board? Yeah. I'm sincerely sorry. Hopefully it was nothing that's going to injure you. Now, we're going to talk about 4 things. We're going to talk about motion. We're going to talk about arrangement. This is new. And we're going to talk about attractive forces.
Is it like a chart?
Yep, I'm going to turn it into a table. And we're going to do it, I guess we'll start with gases first since we've already done that one. And then we'll talk about liquids. And then we'll do solids.
Okay, I'm gonna draw a big chart.
Those of you write bigger might want to make it bigger. Some boxes will have less written in it. Some boxes will have more written in it.
Okay. Gases and what?
Liquids and solids. Now, what do you know about the motion of a gas when compared to a solid and a liquid? It can move anywhere, okay?
Go around.
Okay. Can go around. Is it fast or is it slow?
It's fast.
Okay. All right, so what's its arrangement like? Does it have an arrangement? There's no arrangement at all. Is it close together or far apart? All right, there are attractive forces. What attractive forces am I talking about when I talk about attractive forces? First of all, anybody know? I'm talking about the last unit we studied. So what attractive forces do we study in the last unit? It was a type of bond, not ionic. It was a type in covalent bonds. All right, it went with polar forces. What? Dipole was one. London dispersion was one. What was the other? Hydrogen bonding. All right, so we got dipole, London dispersion, and hydrogen bonding. So, what can you tell me about those attractive forces for a gas? Would they be strong or would they be weak? All right, these are going to be the weakest. And why would gases have the weakest of the attractive forces? That's exactly right. They're the weakest because they are the farthest apart. Okay, they're the weakest because they're the farthest apart. Now, how does a liquid compare to that? All right, what happens to the motion of a liquid when you compare that to a gas? All right, it's going to be slower. Can they move around and go anywhere? Mm-hmm. They can still move anywhere and go around. But the difference between a gas and a liquid is sort of like right now if you went up the main hall, is there anybody in the way?
No.
No, because the bell hasn't rang. It'd be pretty easy to go up and down the main hall. That's a gas. But if I made you wait until the bell rang and then I said go up the main hall, it would be like what? Crowded. All those people would be in your way. That's a liquid. You'd have to move around everybody and shove people out of your way. Okay? How's the arrangement for a liquid? Is there an arrangement?
No.
No. Okay? There's still no arrangement. But this time, it's very crowded and they're pushed together. And what can you tell me about the attractive forces? And we'll stop there. All right. They're stronger than, all right, they're stronger than a gas. And that again is due to closeness. Now, what's our homework? Study for the test. All right, put my calculators in the tub while I go tell that young lady that Miss Crump's going to come back and see better here.
The water's still
You need talk.
All right, get my calculators up here.